Okay, I finished the Rosenblum and Kuttner book on the quantum enigma. This one. I am going to have to read it through from beginning to end again, but I think there's some things I can say as a preliminary at least. Some time ago, maybe a year or two, I mentioned in one of my rambling blogs a question about the double slit, whether it had been done with neutral atoms or not. According to this, they have. He doesn't explain the details. Well, he does and he doesn't. Or I should say they do and they don't, since it's two authors. I'll get to that later. But on page 153, they write, Austrian physicist Anton Zeilinger has done this with large molecules containing 70 carbon atoms, football-shaped buckyballs. He's now setting up to do the same thing with mid-sized proteins and a virus. At a recent conference he was asked, what's the limit? And his answer was, only a budget. So, that would seem to answer my question in the positive. It has been demonstrated with neutral atoms. Although he doesn't say specifically neutral. And I personally do think that there's something special about charged particles as opposed to neutral ones. I don't know. You know? I can't see how you do the experiment with a neutral atom, multiple atoms, molecules. Unless they have a charge on them, I don't see how you get them to travel. Now, what they focus on in this book is a variation of the two-slit experiment, which is fascinating. And it cries out for a really good quality, not just illustration, but animated illustration, which unfortunately is beyond my video making repertoire, at least in a reasonable time period. I suppose I could do it sometime by next year if I were to work on it from now until next year. And even more unfortunately, the illustrations in the book are not very good. I can hopefully put them up here as I talk about them, and you'll see those, and maybe I can make them more clear than they do, but then again, maybe not. I don't know what's going to happen here. Basically, the concept is that you do this a lot of times. You have a wave splitter or a mirror that sends a wave, if it were a wave, in two directions, into closed boxes where there are mirrors that keep the particle in motion until you open one end. They call these box pairs. You set up a lot of them, maybe 1,000. Now what they claim is that this has been done. They claim it has been done with atoms, not just photons or electrons. So they are quite adamant in maintaining that everything they have described is data, indisputable, repeatable data. It isn't theory. So let me explain. Well, let me use their own words. Let me just read the book. To display the quantum enigma, it is not necessary to tell how our box pairs are prepared. However, since we've already spoken of wave functions, we will describe the preparation. After that, however, we will display the quantum enigma, telling only what you would actually see. We will describe the box pairs experiment without mentioning quantum theory or wave functions, without even mentioning waves. Here's how the atoms were put into the box pairs. Any wave can be reflected. A semi-transparent mirror reflects part of a wave and allows the rest to go through. A glass window pane, for example, allows some light through and reflects some. At the glass, the wave function of each individual photon splits. Part of the photon wave function is reflected and part is transmitted. We can also have a semi-transparent mirror for atoms. It splits an atom's wave function into two wave packets. One packet goes through and another is reflected. Unfortunately, I don't know how you do that. They just say that they can do that. I believe them, I just don't know how they do it. So, actually I have some vague ideas, but that's my imagination at work. Just putting together what I know about this and what I know about that, and then saying, well, maybe. But that's as close as I can get. Anyway, continuing. The arrangement of mirrors and boxes in figure 7.4, which I'm hoping is going to be on the screen, allows for the trapping of the two pairs of an atom's wave function in a pair of boxes. We send in a single atom at a known speed and close the doors of the boxes when the wave function packets are inside the boxes. After that, each part of the wave function bounces back and forth in its box. We know there is one and only one atom in each box pair because we observed an atom and sent one into each box pair. Holding an atom in a box without disturbing its wave function would be tricky, but it's certainly doable. Dividing the wave function of an atom into well-separated regions is accomplished in every actual interference experiment with atoms. Capturing the atoms in physical boxes is actually not needed for our demonstration. A defined region of space would be enough. We like to think of each region defined by a box because it's more like a shell game. We can then consider the atom sitting there waiting for us to choose what to do with it rather than have the atom zip through a two-slit diaphragm on its way to the detection screen. Now, basically, they offer two experiments which come down to three choices. You can open the top box, you can open the bottom box, or you can open them both at the same time. Which you do is up to you. And what they show is that whenever you open the top box, it either has an atom in it or it doesn't. If it has an atom in it, then the bottom box will not have an atom in it. If you open the bottom box and it has an atom in it, then the top box will not have an atom in it. But if you open both boxes at the same time, what you'll end up with is an interference pattern showing that there was an atom in both boxes. Even more interesting is if you vary the distance of the boxes, okay, you will vary the interference pattern, showing that the two parts of the atom, or the wave function, as it were, actually knows about the other part. Now, in both cases, this is being detected on a screen. Okay, when you open the box, the thing flies out, and it's being detected on the screen. Okay, so it can form a pattern. Now, if you're doing one box at a time, you don't get any interference pattern. You don't see that. You just see, what do you call it? A spreading of intensity from the most intense region to the outer regions. You know what I mean? Another interesting thing they describe is called complementarity. Suppose you have 1,000 of these box pairs, and you go through each one, opening them one at a time. About half the time you'll see an atom, and about half the time you won't. So when you've seen the atom, you know that there is no atom in the other box, right? And if you don't see an atom, you know that there is an atom in the other box. So take all the empty boxes away, and you know that each box pair you have has an atom in it. Or rather, you have 500 boxes, and you know that each one has an atom in it. Okay? Now I'll read it. I'll read what they said. Okay, so you have 500 boxes, and you know there's an atom in each one. Attempt an interference experiment with these 500 box pairs. An interference pattern would prove that each of those atoms had been simultaneously in both boxes of its pair. But for these box pairs, you had already determined that each atom was wholly in a single box. Finding the interference pattern would therefore show an inconsistency in quantum theory. In fact, these supposedly undisturbed atoms do not produce an interference pattern. What caused these undisturbed atoms to adopt a different behavior? After all, if you had done an interference experiment before you looked in the empty boxes, these same atoms would have produced an interference pattern. Fascinating, isn't it? So I think that's all I'm going to cover this time. I still have the other book to get through, and I have a lot more putting together of thoughts to do. But having established that a thing can be in two places at the same time, to me suggests things about causality. But I'm not ready to say exactly what it suggests.